Hello students, I hope all of you are well today. So I welcome all of you in my second lecture. Today we are going to discuss about the application of Cauchy's theorem and Cauchy's integral theorem along with many solved questions for your practice purpose. So again I am telling you, if you want to learn the topic, please do not skip the video, go until end, so you will grab all the concepts and you will be able to solve all the problems very easily. And this topic is very important for your semester exam, so please be ready with this topic. So now before we start, first of all we need to understand the first concept of this whole discussion, that is the Cauchy's theorem. It is one of the most important theorem in the complex analysis in the viewpoint of the integration, complex integration. So suppose we are having one function f of z, and that function f of z is analytic. Along with another condition is imposed, that is the derivative of the function, that is f dash z, is continuous in a simply connected region capital D. So two conditions I have told you. First of all, the function f of z must be analytic. Second condition, f dash z is continuous in a simply connected region D. The simply connected region, I have made one video for these different types of curves and region in the complex plane. So you can just go and check the lecture 1 for this complex integration series. Now if both the conditions are satisfied, then for any simple closed curve C in D, the value of the integration of f of z over the closed curve capital C is going to be 0 only. So this is one of the most important result we are having in case of the Cauchy's theorem. So let us try to understand this concept. So suppose what it says, say we are having I will try to draw the diagram for your understanding. So suppose we are having a real axis and imaginary axis here. So now if we are having any region that is enclosed by a simple closed curve C, always remember the orientation of the curve should be in the anti-clockwise direction. So now in this region, if we see that the function f of z is analytic, along with that the function f dash z is continuous within this region which is enclosed by the simple closed curve C. So the integration value of fz dz is going to be 0 over this curve. Now another theorem is there, that is the little bit more simplification version of the Cauchy's theorem, that is known as the Cauchy-Gorat theorem. So for Cauchy-Gorat theorem, it is said that suppose if we are having a analytic function f of z and it is analytic over a simply connected region D, then for every simple closed curve C in D, integration of fz dz over this closed curve is going to be 0. So in Cauchy-Gorat theorem, little bit relaxation we have given from the previous condition, that is f dash z is continuous, that condition has been relaxed. So here it says that if we are having one analytic function within and on a simple connected region D, then we can straightforward say that the value of the integration over this region is going to be 0. Now let us come to discuss about the some 2-3 properties of this Cauchy's theorem or Cauchy-Gorat theorem. Sometimes Cauchy-Gorat theorem is also known as the Cauchy's theorem itself. Now suppose we are having the first property, that if function f of z is analytic in a simply connected region D, then the integral of f of z joining any 2 points z0 and z1 in D is independent of the path. It is very important part of the Cauchy's theorem or application of the Cauchy's theorem. So it says that, suppose let us try to visualize it so that the thing will be clear to all of you. So here if we draw, say this is our imaginary axis and this is our real axis. Okay, now we are having one simply connected region. Say we are having one simply connected region which is enclosed by a curve C which is taken in the anti-clockwise sense, and throughout this region the function is analytic. Now suppose within this region we are considering any two different points. Say the first point is z0, second point is z1. Whatever the place of these 2 points can be there inside this region. Now the property of the Cauchy's theorem says that if we are having any 2 points within this region and we want to join these 2 points by any kind of curves, suppose we are having one straight line joining z1 and z0 and z1, another line we are having like this, that is joining z0 z1, another line we are having like this. So whatever path you choose to join these 2 points z0 and z1, the Cauchy's theorem says that this line joining, the integration for line joining z0 and z1 will be independent of the path that we are choosing. Now let us come to the next property of the Cauchy's theorem. So it says that suppose we are having a multiply connected region with outer boundary curve C1 and inner boundary curve C2. Say for your understanding again, I am drawing one graph. So here it is. So this is, suppose there is a real axis and this is the imaginary axis. Now here D is a multiply connected region. About the multiply connected region also you can check out the previous video lecture. So suppose we are having one multiply connected region. Let us draw it. So for your understanding I am just drawing one doubly connected region. Say this is the multiply connected region and this is the domain inside that we are the function f of z is analytic, right? Now the outer boundary it says that the outer boundary of the curve is C1 and the inner boundary curve is C2. So if you want to integrate the function over these two curves, then the value of the integration of fz dz will be same. There will be no change in the values of the integration wherever you want to perform the integration on the outside curve or in the inside curve, because the function is analytic within this annular region. Now let us come to some useful formulas that we are having with us, and these are very useful for solving some practice problems. So the first formula says that integration over the closed curve C dz upon z minus z0, this value must be going to be 0. That is, if C is any closed curve and z equals to z0 is an exterior point of the curve C. So basically this is coming from the direct concept of the Cauchy's theorem. So those things which we are going to explain later in the applications of the Cauchy's theorem while we do the problems. The second property says that we are having integration over the closed curve C dz upon z minus z0. The value of this integration must be equals to 2 pi I, where this point z0 is nothing but is an interior point of the curve. Okay, this is the interior point. Now the third point, third property is that integration over the curve C dz upon z minus z0 whole to the power n, this value is also going to be 0 whenever z minus z equals to z0 is also an interior point of the curve C, simple closed curve C. So basically the property number 2 and property number 3 that already we have proved in the previous video lecture. So you can check and get the solution for these two properties, property number 2 and property number 3. Now let us try to come to discuss some problems based on the Cauchy's theorem first. So first, let us in the exam what type of questions we are going to face. So here one integration has been given, that is integration over a closed curve C 3z square minus 2 divided by z minus 1 dz, where the C is nothing but a circle mod of Z equals to 1 by 2. In the last video lecture already I have told you about the structure mod of Z equals to 1 by 2. So the general form of a circle in the complex plane that we write down in the form of Z minus alpha equal to R, where alpha is the center and R is the radius, that we have discussed in the previous video lecture already. So now this type of problem, whenever you are having, your first task is to draw this circle. Okay, so let us try to draw the circle. So this is our real and imaginary axis. This is our real and imaginary axis. Now we are having mod Z equals to 1 by 2. So if we just match this form with this form, so we will be able to understand that alpha equals to 0 here and radius equals to 1 by 2. So this is a circle which is centered at 0 and having radius 1 by 2. So we are having the center here, the center is at 0 and the radius of the circle is 1 by 2. So it will go here in plus 1 by 2 and it is minus 1 by 2. So this is the circle. Okay, so this is the circle over which we have to perform the integration. So this circle drawing is the first priority of all the complex integrations that we are going to learn in this whole unit. Now let us come to the solution part. So first of all, after drawing the circle, we have to understand the structure of the function. So here the function is given as a 3z square minus 2 divided by z minus 1. Right? So now here if we consider this function as our f of z, so this function is undefined at which point? This function undefined at z equal to 1. So if the function is undefined at z equal to 1, that means it will fail to satisfy the condition of analyticity. So the function is not analytic at the point z equal to 1 only, except for z equal to 1. If you put any other point, then the function is just like a fractional rational function. So it will be analytic everywhere except the point z equal to 1. Now this point z equal to 1, where it fits? Z equal to 1 fits outside the circle, right now. So here for the given integration we have seen this is the circle and z equal to 1, this point will be outside the circle. So if we are having z equal to 1 outside the circle, so inside the circle and on the boundary of the circle there is no problem, right? Inside the circle and in the boundary of the circle there is no problem for maintaining the analytic condition. So using the Cauchy's theorem, what we can say, that using Cauchy's theorem, integration of fz dz over this closed curve, the value is going to be 0 only, because the function is analytic within and on this simple closed curve. Let us come to the second question. So the second question says that we want to evaluate another function e power minus z upon z plus 1 dz, where the same type of function the curve is given mod z equals to 1 by 2. So again we have to draw the diagram. So every time whatever the circle is given to us, mostly you will get the circle in the exam only. So suppose here center is at the point z equal to 0 and the radius is 1 by 2 and here it is also minus 1 by 2. So this will be the portion of the circle, right? So this is the portion of the circle. Now we have to look at into the functional structure. So in this function we can see that the structure is e power minus z upon z plus 1, right? So this function is going to be non-analytic at which point? At z equal to minus 1, because it is fails to satisfy the existence of the function. If we put z equal to minus 1, the function will be undefined. So if it is undefined, there is no question for understanding the case of the analyticity. So z equal to minus 1, now it lies outside the region of the function right now. outside the region of the integration. There is a circle, so -1 basically lies here. So the problem of the analyticity lies outside the domain. It is not lying inside the circle. There is no problem to be analytic within and on this circle. Therefore, it satisfies the condition of the Cauchy's theorem. That is, the function is analytic within and on this region which is bounded by this curve C mod z equal to 1 by 2. Therefore, using Cauchy's theorem also we can say the result is going to be 0 only. So basically the Cauchy's theorem concept is that whenever we have to understand the function where it is fails to satisfy the condition of analyticity, that point should be an exterior point of the simply connected region. Then only inside and on the boundary of the simply connected region the function will be fully analytic and the result is going to be 0. Similarly, we are having the third question. That is also a very simple question. You can understand it very easily. So here what it says, we have to evaluate integration over C z plus 1 whole cube dz, where C is the boundary of the rectangle having the vertices a plus ib, minus a plus ib, minus a minus ib and a minus ib. So let us draw. Whenever you are having any kind of question like this, I have told you that first work you have to do, that is the drawing of the region. So this is imaginary axis, this is our real axis, a plus ib. So a plus ib will be a point here, one vertex, that is the point a plus ib. The second vertex is minus a plus ib, so it will be minus a means in the negative side of real axis. So minus a plus ib, this is our real axis. Then minus a minus ib, so this is minus a minus ib, and thereafter we are having a minus ib, right? So we have to join all these vertices so that we will form one rectangle. So this is the curve, except of circle, here it is given as a rectangle. So now the function whatever it is given here, there is no denominator. Have you seen this? That is z plus 1 whole cube is given, so there is no denominator. So since there is no denominator, there will be no problem to satisfy the condition of analyticity, because it is an entire function, it is a polynomial function, it is entire, that means it is analytic in the whole complex plane without any singularities. So therefore this function is analytic, therefore hence this will be analytic within and on this region also, right, on the boundary along in this region. Therefore by applying the Cauchy's theorem we can say the value of the integration is also equals to 0. I think you have understood. Now we are going to discuss about the next formula, that is the Cauchy's integral formula. That is one of the most important formula that we are having in the complex integration. So here the condition is that suppose we are having a function f of z which is analytic in a simply connected region D. Then for any simple closed curve C in D with z equal to z0 as an interior point, then the value of this integration is going to be like this. That is integration over C f of z by z minus z0 dz. This is going to be 2 pi I multiplied with the functional value at a point z0. Now we also have another form, that is the nth order derivative of the function, that is integration over C fz upon z minus z0 whole to the power n plus 1 dz equal to 2 pi I divided by n factorial multiplied with nth order derivative of f at a point z equal to z0. So let us try to understand what it's try to say. Cauchy's integral theorem or Cauchy's integral formula. So here suppose we are having the imaginary axis and here we are having the real axis. Okay, now we are going to draw one simply connected region say this is a simply connected region which is enclosed by a curve capital C. Now for this one, z equal to z0 is an interior point. So for Cauchy's theorem previous, what we have learned, it should be an exterior point, then the value of the integration is going to be 0 only. But here z equal to z0 basically is an interior point. So if it is an interior point, then we can do the integration in this manner. We will make a circle, and in this annular portion we will do the integration. The proof I am not doing here. If you want, I can do it later. So now using this concept, the value of this integration is going to be 2 pi I into functional value at z0, and if we are having nth order derivative, then the result is 2 pi I by n factorial f to the power n z0. Now let us try to understand some questions from here. So the first problem is that evaluate the value of the integration 3z square plus z, 3z square plus z divided by z square minus 1, where we are having the circle z minus 1 equal to 1. So first of all, what I have told you, that whatever question will be given to us, we have to draw the diagram of the region or the circle. So here it is our real axis, here it is our imaginary axis. Now here you can see the center of the circle is at a point 1, and also the radius is 1. So on the real axis, the center 1, it will come, now it will go to radius 1, so it will come to 2 here, and it will come to 0 here. So this will be the portion of the circle. Okay, because the center and the radius is changing now, that's why we are having this type of diagram. Okay, so this is the actual curve over which we have to perform this integration. This is the curve C. Now we will come to the solution part. Since you can see the structure of this 3z square plus z by z square minus 1 is not in the form of the above. What we have seen in the structure is f of z divided by z minus z0, one single factor, otherwise the single factor to the power some order, some power will be there, n plus 1, that is a square, cube, something like that. But here we are having 3z square plus z divided by z square minus 1. So z square minus 1 we can split into z plus 1, z minus 1. So first of all, we have to rearrange this integration into the form of the Cauchy's integral formula, either form 1 or form 2. So for that we have to do the partial fraction. So 3z square plus z, this part we will not touch. This part is going to be our f of z. Except of f of z, the remaining part is 1 upon z plus 1, z minus 1. So since these two are the linear factors, we have the partial fraction in this manner: a upon z plus 1 plus b upon z minus 1. Now if we write down, then cross multiply, we are having 1 equals to a into z minus 1 plus b into z plus 1. Now putting different points, suppose we put z equal to 1, so definitely after calculation we will get the value of b equal to 1 by 2, and by putting z equal to minus 1, we are having a equal to minus 1 by 2. So this partial fraction can take the form minus 1 by 2 by z plus 1 and plus 1 by 2 by z minus 1, right? So this structure can be written in the form of this 3z square plus z by z square minus 1 dz. It can be written in this form, in this structure, just by putting the values in the partial fraction. Now look at the both integrations. So if we just look at the both integration, what we can see, that for this integration z equal to minus 1 will create the problem. If we put z equal to minus 1, the function is going to be not analytic, and if we put z equal to 1 for this one, this will create the problem for the second integration, right? Now if we look at the circle, z equal to 1 lies inside the circle, right? But z equal to minus 1, where it will lie? Z equal to minus 1 lies outside the circle. It is not inside the circle, it is outside the circle. So since it is outside the circle, so any point which is lies outside the domain, for that we have to apply the Cauchy's theorem. That is the first theorem that we have learned today. So using Cauchy's theorem, the value of the first integration, it is going to be 0 only, right? Now for the second theorem, we have to apply the Cauchy's integral formula. Since z equal to 1 lies inside the domain, that I have written, z equal to 1 lies inside the circle and z equal to minus 1 lies outside the circle. So for interior point, we have to apply Cauchy's integral formula. For exterior point, we have to apply the Cauchy's formula, right? Now by Cauchy's integral formula, what we have? So this is 1 by 2 integration 3z square plus z upon z minus 1 dz. This is going to be 1 by 2. 2 pi I, 1 by 2 is coming from here. Value of this integration is 2 pi I into functional value at that particular point, which is the interior point, right? So f of 1, how we will get f of 1? Already I have told you, whatever will be there in the numerator in the Cauchy's integral formula, that will be your function. So 3z square plus z, it is your function f of z. So put z equal to 1 in this function. We are having the answer of this integration as 4 pi I. Now let us come to the next question. That is very, very important for exam. Evaluate the integration over C cos pi z square plus sin pi z square divided by z minus 1 z minus 2, where we are having the circle mod z equal to 3. So let us try to draw the diagram first. So here we are having our imaginary axis, here we are having our real axis. Now mod z equal to 3, since it is given, so the center of this circle is at the point z equal to 0, and the radius of the circle is plus 3 here and minus 3 here, right? So this is the whole range of this circle. This is the whole range of this circle. Now again, it is not in the structure of the Cauchy's integral formula. So we have to first do the partial fraction. In a similar way that we have done the partial fraction for the previous question, we have done in the same manner. So we have the partial fraction and the values of a and b. So after getting this, we are splitting the integration into two parts as per the partial fraction. So for the first case, we see the first integration will getting some problem by putting z equal to 1, which is an interior point, not an exterior point. And also for the second integration, we are having z minus 2. So by putting z equal to 2, again we will have some problem. So both the points 1 and 2 are the interior point now, not for the previous question. For previous question, one point is outside, one point is inside, but here both the points lies inside the region. So if both the points are lies inside the region, we have to apply the Cauchy's integral formula for both the integrations separately. So how to do this? So for the first integration, we are having the minus sign I have taken already because it is there. So minus of this equals to minus 2 pi I into f of 1, because here 1 is the interior point. So our function is cos pi z square plus sin pi z square. So put z equal to 1, we have cos pi plus sin pi. All you know that cos pi equal to minus 1 and sin pi equals to 0. So this part is going to be 0 and this pi is minus 1. So we are having 2 pi I. Similarly, we are having for the second one 2 pi I into f of 2, because 2 is the interior point. Now we are putting z equal to 2, so it is coming cos 4 pi plus sin 4 pi. So sin n pi is always 0 for n is integer, and cos 4 pi equals to 1 plus 1. So we are having 2 pi I. So ultimately what is the result? So whenever we joined both the values of the integration, we are having the answer as 4 pi I. Okay, so this type of problem basically we are going to face. So both the problems that we have done here, it is for the applying the first formula of the Cauchy's integral theorem. Now let us try to understand the second formula for the Cauchy's integral theorem. Evaluate z into e power 2z upon z minus 1 whole cube. So here you can see the power is coming. For the previous two question, in the denominator we are having linear factors, right? The powers of the factors are linear, but here we are having power more than 1, that is 3 is there. So if we just compare this with the Cauchy's integral formula form, what is the form? That is integration over c f of z divided by z minus z0 whole to the power n plus 1 dz. This is the structure, second structure. So if we just compare n plus 1 with 3, so n value is our 2. Remember this, okay? N value equals to 2 here. Now again we have to draw the circle first. So here this is our real imaginary axis, and this is our real axis. Now here you can see z plus I is given. The circle structure is z minus alpha equal to r. So if we compare with this form, what is the value of alpha? Alpha equals to minus I. So here the center lies in the imaginary axis, right? Center lie in the imaginary axis. So here it is minus I, and r radius equal to 2. So for 2 radius it will go minus I, then it will go up to minus 3I, and it will go up to plus I because it is 0 and plus I. So this is going to be your whole circle over which we have to perform the integration. So definitely z equal to 1, for which the problem will occur, it will come inside the circle, right? Z equal to 1, it will come inside the circle. So since it is an interior point, so what we can say, using the Cauchy's formula, Cauchy integral formula, this can be 2 pi I divided by n factorial into f to the power n at z0. So if we match this thing, n equal to 2 here, 2 pi I by 2 factorial f double dashed at the point 1. So we have to just find out the double derivative of f dashed z and f double dashed of z. Here we have applied the u into v rule of derivative. So after applying the double derivative and putting value z equal to 1, we are having 8e square. So simply substitute this value here. We have 2 pi I upon 2 factorial into 8e square. So result is 8e square into pi I. Okay, 8e square into pi I. Similarly, I am having the next question. I am leaving this question for you. You just try to understand it, and if you are not be able to understand also, you let me know. We can explain it later. Similar question, same type of question, thoroughly you just go through it, then you will be able to understand. Now we come to the end of this lecture, that with the Moreira's theorem, which is known as the converse of the Cauchy's theorem. So in Cauchy's theorem, what we have learned, that if we are having an analytic function within and on a simple connected region D, then the value of the integration of f of z over the curve is going to be 0. The converse of the Cauchy's theorem says that if we are having suppose if we are having one continuous function over a simple connected domain D, also we see the value of this integration is 0 over the curve C, then the function is going to be analytic. Okay, so this is the converse part. So for Cauchy's theorem, it is initially given it is analytic function, then the value of the integration is coming 0. For converse of Cauchy's theorem says that function is continuous and value of the integration is given as 0 already. So from there what we can conclude, the conclusion will be function is analytic. Okay, so with this we are going to close this session. So if you understand the topic, please subscribe the channel and share and like.